Model 1, M/M/1, Infinity/FIFO model. This is a simple queue with Poisson arrival, exponential service time, single server, infinite capacity, and first in first out discipline. Steady-state probabilities. The steady-state probabilities for n customers in the system is P0 is equal to 1 minus lambda by mu, and Pn is equal to lambda by mu whole power n into 1 minus lambda by mu. N is greater than or equal to 1. Characteristic of the queue. Average number of customers in the system. LS is equal to lambda by mu minus lambda. Average number of customers in the queue. LQ is equal to lambda square by mu into mu minus lambda. Average number of customers in non-empty queues. LW is equal to mu by mu minus lambda. Probability that the number of customers in the system exceeds K, P of n greater K is equal to lambda by mu whole power K plus 1, where n is the number of customers in the system. Probability density function of the waiting time in the system. F of W is equal to mu minus lambda into e power minus of mu minus lambda into W, average waiting time of a customer in the system. E of Ws is equal to 1 by mu minus lambda. Probability that the waiting time of a customers in the system exceeds T, P of Ws greater than T is equal to e power minus of mu minus lambda into T, probability density function of the waiting time in the queue. G of W is equal to lambda by mu into mu minus lambda e power minus of mu minus lambda into W if W greater than 0. 1 minus lambda by mu if W is equal to 0. Average waiting time of a customers in the queue. E of WQ is equal to lambda by mu into mu minus lambda. Average waiting time of a customer in the queue, if he has to wait. E of WQ, given that W greater than 0, is equal to 1 by mu minus lambda. Relation among E of NS, E of NQ, E of WS and E of WQ. E of NS is equal to lambda by mu minus lambda is equal to lambda into E of WS. E of NQ is equal to lambda square by mu into mu minus lambda is equal to lambda into E of WQ. E of WS is equal to E of WQ plus 1 by mu. E of NS is equal to E of NQ plus lambda by mu. Arrivals at a telephone booth are considered to be Poisson with an average time of 12 minutes between one arrival and the next. The length of a phone call is assumed to be distributed exponentially with mean 4 minutes. A. Find the average number of persons waiting in the system. B. What is the probability that a person arriving at the booth will have to wait in the queue? C. What is the probability that it will take him more than 10 minutes altogether to wait for the phone and complete his call? D. Estimate the fraction of the day when the phone will be in use. E. The telephone department will install a second booth, when convinced that an arrival has to wait on the average for at least 3 minutes for phone. By how much the flow of arrivals should increase in order to justify a second booth? F. What is the average length of the queue that forms from time to time? Solution. Given lambda is equal to 1 by 12 per minute and mu is equal to 1 by 4 per hour. A. Average number of persons waiting in the system. E of ns is equal to lambda by mu minus lambda. Implies E of ns is equal to 1 by 12 by 1 by 4 minus 1 by 12 is equal to 0.5 customers. B. P of a customer has to wait is equal to P of W greater than 0 is equal to 1 minus P of W is equal to 0. That is, P of W greater than 0 is equal to 1, P0 is equal to lambda by mu is equal to 1 by 3. C. P of Ws greater than T is equal to e power minus of mu minus lambda into T. Implies P of Ws greater than 10 is equal to e power minus of 1 by 4 minus 1 by 12 into 10 is equal to e power minus of 5 by 3 is equal to 0.1889. D. P of the phone will be idle is equal to P of n is equal to 0 is equal to P0 is equal to 1 minus lambda by mu is equal to 2 by 3. Therefore, P of the phone will be busy is equal to 1 minus 2 by 3 is equal to 1 by 3. Hence the fraction of the day when the phone will be in use is 1 by 3. E. The second phone will installed if E of WQ greater than 3 minutes. That is, lambda r by mu into mu minus lambda r greater than 3 implies lambda r greater than 3 by 4 into 1 by 4 minus lambda r. Implies lambda r greater than 3 by 28. Hence, the arrival rate should increase by 3 by 28 minus 1 by 12 is equal to 1 by 42 per minute. F. E of NQ, given that the Q is always available, is equal to E of NQ, given that NQ greater than 0 is equal to mu by mu minus lambda. Implies E of NQ, given that NQ greater than 0 is equal to 1 by 4 by 1 by 4 minus 1 by 12 is equal to 1.5 persons. Customers arrive at a one-man barber shop according to a Poisson process with a mean inter-arrival time of 12 minutes. Customers spend an average of 10 minutes in the barber's chair. A. What is the expected number of customers in the barber shop and in the queue? B. Calculate the percentage of time an arrival can walk straight into the barber's chair without having to wait. C. How much time can a customer expect to spend in the barber shop? D. Management will provide another chair and hire another barber when a customer's waiting time in the shop exceeds 1.25 h. How much must be average rate of arrivals increase to warrant a second barber? E. What is the average time customers spend in the queue? F. What is the probability that the waiting time in the system is greater than 30 minutes? G. Calculate the percentage of customers who have to wait prior to getting into the barber's chair. H. What is the probability that more than 3 customers are in the system? Solution. Given lambda is equal to 1 by 12 per minute and mu is equal to 1 by 10 per minute. A. Expected number of customers in the barber shop, E of ns is equal to lambda by mu lambda. Implies E of ns is equal to 1 by 12 divided by 1 by 10 minus 1 by 12 is equal to 5 customers. Expected number of customers in the queue, E of nq is equal to lambda square by mu into mu minus lambda. Implies E of nq is equal to 1 by 144, divided by 1 by 10 into 1 by 10 minus 1 by 12 is equal to 4.17 customers. B. Probability that a customer straight goes to the barber's chair is equal to probability that no customers in the system is equal to P0. Implies P0 is equal to 1 minus lambda by mu is equal to 1 minus 1 by 12, divided by 1 by 10 is equal to 1 by 6. Therefore, percentage of time an arrival need not wait is equal to 16.67. G. Probability that a customer has to wait is equal to P of W greater than 0 is equal to 1 minus P of W is equal to 0 is equal to 1 minus P0. Implies P of W greater than 0 is equal to lambda by mu is equal to 1 by 12 divided by 1 by 10 is equal to 5 by 6. Therefore, percentage of customers who have to wait is equal to 5 by 6 into 100 is equal to 83.33%. H. P of n greater than 3 is equal to P4 plus P5 plus P6 plus etc. is equal to 1 minus of P0 plus P1 plus P2 plus P3. We know that Pn is equal to 1 minus lambda by mu into lambda by mu whole power n for n greater than or equal to 0. P of n greater than 3 is equal to 1 minus lambda by mu into 1 plus lambda by mu plus lambda by mu whole square plus lambda by mu whole cube is equal to 1 minus lambda by mu minus lambda by mu whole square minus lambda by mu whole cube plus lambda by mu minus lambda by mu whole square plus lambda by mu whole cube plus lambda by mu whole power 4 is equal to lambda by mu whole power 4 is equal to 5 by 6 whole power 4 is equal to 0.4823.